Hi, my name is Chao. Today, in this video, we'll talk about two awesome applications of group theory. And for definitions and basic examples of groups, and for more detailed information, you can refer to the extended abstract. So before we get started, let's start with two important groups. The first one is the permutation group. Let X be a finite set of n elements, and let G be the set of all bijective functions from X to X, with the operation defined to be function composition. So this pair, G composition, forms a group, and we call this permutation group of order n. We write as Sn. The second group is the symmetry group. So we start with S, an object, for example, an image, and we let G be the set of all transformations under which S is invariant. And with operation transformation composition, this pairing G composition forms a group. We call it the symmetry group of that object S. So equipped with these two examples, we're ready to get started. Our first example is the wallpaper. So as if we see wallpapers at different places, oftentimes they look different. So we might start thinking there are infinite many types of wallpapers. It turns out that this is wrong. So we can actually put a group structure on wallpaper. We call them wallpaper group, or plane symmetry group, whose elements are isometries, i.e. translations, rotations, reflections, and neglect reflections. The Russian mathematician Evgraf proved that there are only 17 possible wallpaper groups, i.e. there are only 17 possible wallpaper. And here is the complete list. That means any wallpaper we have seen, no matter how different they look like, is just one of the variations of one of the 17 patterns in the list. And now let's start a sketch of the proof. So firstly, we need to define a new group. So we're collecting all the 2 by 2 matrices such that M transpose M equals the identity matrix. So this is called a orthogonal group. Next, if we let G be the wallpaper group, we define G naught to be the point group G, such that its elements are A, picking from the orthogonal group which is defined above, such that AX plus B belongs G for any X in R2 and some B from R. So next one, if we let T be the translation group, now together with the G naught and G, we can compute the H2 G naught G T. This is so-called the second cohomology group. So this is a abelian group such that allow us to write down all the possibilities of the wallpaper groups. So it turns out that only 17 of them, as previously mentioned. So that's the basic strategy of classifying all of the wallpapers. So those beautiful works of art, wallpaper art, illustrate very nicely the group theoretic aspects of symmetry group. On the other hand, studying the symmetry group allows us to find more geometric restrictions such that the artists have to work out when they are creating their beautiful patterns. So they benefit both ways. So this is the end of our first example. Okay, so now let's move on to our second example, which are relates to solutions to polynomials. So before we start, let's see some terminologies. So when we say quadratic, cubic, quartic, and quintic, they just mean polynomials with degree 2, degree 3, degree 4, and degree 5, respectively. So another bit of math you may still remember from high school is the famous quadratic equation. So we're solving the quartic equations. So this can be given by finding the determinants, which is known that is a1 squared minus 4a naught, a2. So by using the determinants, you can find all the solutions of the quadratic formula. And it took people a lot of effort to find the solutions to the cubic equation, so which the determinants is slightly more complicated, but people did it. And by combining the ideas and the strategies, people quickly find the solutions to the quartic equation. But this one's determinants is crazily long. It's a bit scary, but all we can do is appreciate the result. So people find the solutions, the general solutions to the quartic equation. But then people keep moving on to solve the quintic equation, which are degree 5 polynomials. But the process stopped. People can never find the solutions no matter how hard we try. Then this problem has been proved later on by using Gawa theory that this one has no general solutions. So in other words, it's not we were too stupid finding the solutions. This is because there aren't any solutions. So specifically, Gawa theory says, so here is the Gawa theory, says a polynomial is solvable, i.e. has general solutions, if and only if its related symmetric group is solvable. So a group G is solvable. We mean there exists a subnormal series such that we have G, G1 all the way to 1, such that in the chain that each quotient is a billion. So it turns out that polynomials of degree 5, i.e. the quintic polynomials, their related symmetric group is A5. So this is the alternating symmetric group of order 5, and it's known fact that this is not a solvable group. Hence, by Gawa theory, polynomials of degree 5 is not solvable, i.e. there does not exist analytic solutions. So this is our second example of applications of group theory.